Hello guys, so welcome back to our analog circuits course. Last time we discussed the current carriers in semiconductors, and we could, using doping, we could increase or improve the number of current carriers in semiconductors. We could increase the number of electrons or the number of holes. When we dope with phosphorus, which has 5 atoms in its valence band, we could increase the number of electrons. When we dope with boron, which has 3 electrons in its valence band, we could increase holes. Okay? And it's time now to highlight how the current, move, or how the electrons move to form a current, of course, inside a semiconductor. Okay? And actually, we have here in semiconductors, we have two main currents. We have what's called the drift current, which is very similar to the current we have in wires, metals, conductors. And we have another current that's called the diffusion current. Okay, we're going to start with the drift current. Okay, to understand the drift current and drive the equations for it, we need to understand what's called drift velocity, which basically, the velocity or the speed of the electron when we apply an electric field or exert electric field on that electron. Okay, so in free space, this is not semiconductor, just a free space. So let's start by this. If we have a free space, nothing, vacuum. Okay, and we put two electrodes like this, positive and negative, there will be electric field between these two electrodes. Okay, and the electric field direction usually from the positive to the negative. Let's call it E. Electric field. Okay. Good. So basically, now we have electric field. Now let's assume that somehow we inject electron between these two electrodes. Here, for example. Now we have a negative charge in a field, in an electric field. What will happen then is that this electric field will exert a force on that electron, and this force will make the electron to move. Okay, so basically the electron will move opposite to the electric field direction from positive to negative, and we know that the electrons moves away from the negative, attracted to the positive. That's why it's opposite. Okay, so basically the electron will move from the negative to the positive, from the negative electrode or toward the positive electrode. Okay, so this electric field and this force, okay, let's call it F, and it's a vector also, equal to minus Q, which is a electron charge, times E. And basically the force is also in the opposite direction of the electron. So this is the direction of the force. And that's intuitive, if you push something in that way, it should move in that way. Okay, and when we say that the electron is moving toward the towards the positive electrode or the positive metal or contact, that means that the force is also in that direction. Okay, that's good. And we know that F is equal to m, the mass of the electron, multiplied by or times the acceleration. This is the acceleration. That means that the electron will move with certain velocity, and this velocity can be changed with time. That's why we can have acceleration. Okay, this is equal to minus QE. Okay, and A the acceleration is equal to dv by dt. What is v? This is the velocity of the charge, and here it's the electron between these two electrodes. Okay, so m dv by dt, and let's now ignore the the vectors for a moment, equal to minus qe, and from that v will be equal to minus q over m, the integral of e dt. Okay, just take the integration of both sides. Okay, and that's if we assume that if E is constant, that's easily can be achieved. I mean, if you put constant potential or constant voltage between these two electrodes, potential is a voltage. If we put a constant voltage between these two electrodes, then the field is constant. You can assure that. Okay, so that means that V will be equal to minus QE over MT. And the minus here means that the electron will move, opposite to the electric field again. So the force, the acceleration, the speed, all these vectors are opposite to the electric field. In case of the electron, I mean negative charge. Okay, so that's me to make it clear. But let's, just look at this equation. That means that the electron will move in a straight line because the electric field is a straight line. Okay. And the speed will change with a constant rate versus time. I mean, for each one second, for example, there will be an equal increment in the speed. Since the speed is incrementing, there will be acceleration and so on. Okay, but that's the free space. That's the ideal case, But in our material, we are concerned with our material, our semiconductor, how the electron will move in a semiconductor. Okay. Basically, the electron inside the material is not alone. There is a world there. There is atoms. And these atoms are vibrating. They have a charge. There are many stuff out there that affect the motion, rather than the free space is just free. Empty. But no, in our semiconductor, it will not the case. It will not be the case. It's much more complicated. So, motion inside a semiconductor. Okay. So, if we assume we have a semiconductor like this, piece of semiconductor, okay, and we just apply some potential, some voltage over the terminals of this sample, then again we will have electric field. And the electric field always from the positive to the negative. Here is the positive, here is the negative. Since there is electric field, now there is a force. And this force can make or will push the electron against the electric field. It will make the electron to move, but against the direction of the electron, just like the free space. But the motion will be in a straight line. It will not be perfect like the free space. So the electron may collide with an atom and deviate, then go back to the course, which is just opposite to the electric field. But there is a positive ion there, and this positive ion we know will attract the electron towards it because it's a positive and the electron is negative, and so on. So there are many deviations, there are many effects in the environment in which the electron is moving. That's why the motion is not that perfect. It's not in a straight line like the free space case. So it may do something like this. So let's draw it with another color, for example. So here is the electron. Let's say this is the electron. So it may move like this, then this, then a little bit backward, a little bit forward, forward again, a little bit backward, until it reaches the positive terminal. If you look here, most of the time, the electron is moving, in the direction from the negative to the positive. I mean, there is a net velocity. All these vectors, if you add them together, you will have a net vector in the direction opposite to the electric field, straight line opposite to the electric field. Okay, that's why the electron can make it from the negative to the negative terminal to the positive terminal, just opposite to the electric field. But it will not be a straight line. It goes up a little, down a little, but all the time, there is a net velocity in the direction of the electric field. Okay. So there are many distractions. So let's say here there are many distractions inside the semiconductor. Okay. We have two major reasons for this. Two major reasons. Number one, atoms vibration, or let's say it more formally, thermal vibrations. Thermal vibrations. So atoms usually, due to thermal energy, and we said last time, if you put a sample in a room and this room has some temperature rather than zero, larger than zero, then you applying some thermal energy to that material. Basically, because if you have a temperature of X, T equal to X, then you have a thermal energy equal to K multiplied by X. K is a Boltzmann constant. So there is always thermal energy, if the temperature, of course, is greater than zero. Okay, and this energy, this thermal energy, when an atom, absorbs some thermal energy, they are not moving, but they are vibrating, going up and down, just like foam vibration. And of course, if the electron was moving and suddenly it hits by an atom, then it will deviate. Okay, or maybe absorb it completely in the atom. So this is number one. Number two, which is really interesting, deviation due to positive ions, or positive ions. So so deviation due to ions. This is more general because holes that have the same problem as well. So let's talk about N-type material. In N-type material, you add phosphorus atom, and this phosphorus atom will lose an electron, and it will become positive ion, right? So let's assume there were an electron like this moving in that direction, straightforward. If it continues, it will continue like this, very straight. Also, due to this positive ion, when it reaches with some distance of this positive ion, there will be electric force. Whenever you have two charges, there will be electric force between them. And in that case, it will be attraction force. So, the electron have now the tendency to continue in its main course, and the tendency to move in that direction toward the positive ion. It will not go in that one, it will not go to the positive ion. It will not continue in its original course, but it will do something like this. something, a net, a net motion. It's not a straightforward, it's not a straight line like it was, and it's not in the direction of the most of IO. Okay, and we have similar situation when we have holes and boron ions, but the boron will be negative now. Okay, so these are the main two, reasons why it's not a straight line motion like free space. So now we have charges that are moving, okay, but they will be distracted, okay. But at the end, there will be a net velocity, and this velocity is opposite to the direction of the electric field, okay, from negative to positive. And this velocity is actually the drift velocity, okay, and they could, drive equations for it, and they found that this drift velocity is just proportional to the applied electric field. And if the electric field is small enough, the relation will be linear. So the drift velocity here of electrons is actually proportional to the electric field. So we can say that V drift equal to some constant, we will call it mu A. And again, both are, vector equation. It's a vector equation. Both are vector quantities. And this mu is called the mobility. That's why they call it mu. Okay, the mobility of the electron. Or the hole. It's general here. And this relation holds, I mean, it's linear when the electric field is small enough. Of course, don't worry about that in the exam or the midterm or quiz. I will tell you that this is large enough or this is small enough. Okay. And it turns out there are two mobilities. I mean, electrons have a mobility that is different from the whole mobility. So we have two equations we can say. We have Vn equal to minus mu E. And why minus? Because this is mu N. This is for electrons. And we have Vb equal to mu B. This is for holes. And why minus? Because electrons moves, opposite to the electric field. So the minus here, because electrons moves opposite to the electric field. But the holes move just from the negative to positive, just like electric field. Okay. So we have mu N and we have mu B. Okay. And basically, for each material, mu N and mu B is constant. It's just a property of the material, just like the energy gap. Okay. So for silicon, for example, silicon mobility or mobilities, because we have two mobilities, mu N equal to 1350 and mu B is equal to 480. And now what is the unit? What is the unit of the mobility? That's very easy. So V is in meter per second. E is volt per meter. Okay. So basically it's meter square over volt second. So I will write it meter square, although it's wrong. So just keep with me, divided by volt second. So basically here meter or centimeter or micrometer, matters a lot. Okay, it's just 100 between them. So basically this is 1350 is measured in centimeters, not meters. So this is centimeter square per volt second. That means that the volt is when they do that measurement, the speed was in centimeter per second, and the electric field was volt per centimeter. And of course, meter and centimeter just matter of each, multiplying by 100 or dividing by 100. And again, for the holes, it's a centimeter square volt second. Okay. Before we continue now, let's see one observation here, that the mu n is much larger than mu b. And that's the fact, basically. Because electrons are moving, remember, electrons are in the conduction band, the carriers, are in the conduction band. And the holes are in the valence band. And remember, in the first place, the conduction band was just free at zero, for example, at 0 Kelvin. It's completely free, right? Then we increase the temperature, we make doping, then we inject electrons into it. But still, it's not filled like the valence band. So electrons, they have more freedom to move in the conduction band. Although holes, which are in the valence band, valence band is almost, has many, has many stuff in it. I mean, it's partially filled. Okay, so the motion there in the valence band is harder than the motion in the conduction band. So why is this? Because motion of the electrons in the conduction band is, much easier, we can say, than the motion of the holes in the valence band. And why is that again? Because the conduction in the valence band is partially filled. Okay, while the conduction band is partially free, while the conduction band is partially free. Okay, guys, that's good. Let's take an example. We have here a silicon sample. This sample has two terminals, A and B. Okay, and we apply 1 volt. We put a battery and we apply 1 volt between these two terminals, such that B is positive and A is negative. The length of this sample is 1 micrometer, and it's N-type, and that's so important. Since we put a voltage, a battery, then a current will flow from the positive terminal to the negative terminal. Okay. And we should expect that since it's N-type, most of this current comes from the electron carriers in the conduction band. And we want to find in that example the drift velocity Vn of these carriers, and also the time for the carriers to move from A to B, not from B to A. Although the current is moving from B to A, but remember, the terminology for the current is that it's a definition, that it's the direction of the positive carriers, although we have here negative carriers. So in that case, it is the opposite to the direction of the electrons. Where the electron will flow, how the electron will flow? They flow towards the positive terminal. So the electron will flow in that direction, from negative to positive, because the electric field is in that direction, from positive to negative. Okay, good. So let's solve it. Let's do it with red, for example. So A, we just need very few equations, so don't think a lot. So Vn equal to mu n E, and here we are concerned about the scalar. We don't want the vector, you know. We just need the scalar value for a Vn. Okay, so do we know mu n? Yes, we know mu n. Do we know E? We don't know E, so we should calculate it. So E is basically equal to the voltage over the distance. So the voltage is 1 volt, and the distance is 1 micrometer. 1 micrometer. This is basically 10 to the power 6 volt per meter. But remember, we like always in that course to make everything in centimeter, you know. So we should convert this into centimeters. So to convert a meter to centimeter, we multiply by 100. So this will be 1 to the power 6, 10 to the power 6 volt. And here is 100 or 10 to the power of 2 centimeter. I'm sorry, centimeter. Yeah, centimeter. So this will be 10 to the power of 4 volt per centimeter. Then Vn equal to 1350 multiplied by 10 to the power of 4. Okay, this will be, you know, very big, you know, 1.35 10 to the power of 7. Okay, and Vn is centimeter now per second. Okay, that's number A. Number B, find the time for carriers to travel from A to B. Okay, we know that the velocity equal to distance over time. Distance over time. This is just basic definition. Okay, so this the distance here is the distance that the electron will move through, which is 1 micrometer, and the time is the required, you know, required metric here, or the required variable. So our unknown. So basically here 135 10 to the power of 7 equal to 1 micrometer, and we should change it. So this is 1 micrometer 10 to the power of minus 6 meter. And to change meter to centimeter, we'll multiply by 100 over the time that is, you know, unknown. Okay, so basically the time will be equal to 7.4 10 to the power of minus 12 second, or 7.4 picosecond. Pico is, you know, 10 to the power of minus 12. Okay, guys. So with this introduction, now we are ready, you know, since we knew how to calculate the drift velocity, now we are ready to calculate the drift current, our first current that can flow in a semiconductor, which is called drift current, which is a current that is that come from or due to the effect of applied voltage. Okay, guys. So see you next time. Bye bye.